As mentioned in the previous section, all crystalline solids can diffract X-rays. Let's compare a crystalline material to a solid brick of 1-inch blocks, assembled with no gaps in between. In this scenario, you can take a ruler and make concrete and definitive statements about distances between any given point on one block and another point on the next block. More easily, we can sit and do a few basic trigonometric exercises to generate a series of distances. One of the strengths of crystalline materials is that there will be multiple instances of a set relationship, both through repetition and through expansion. Repetition is what helps elevate the intensity of diffraction signals in crystalline materials and generate sharp, discrete peaks in a graphic representation, called a diffractogram. The most common and strongest peaks are associated with the sizes of the smallest repeating component of the crystal, called the unit cell, and are labeled as Miller indices. Now, a Miller index is given as a set of 3 numbers corresponding to 3 axes in space, similar to coordinates in the Cartesian system. But these correspond to the space defined by the size and shape of the unit cell. The distance between point 000 and 001 is the same as 001 and 002. However, no individual point in the crystal is actually special. So 001 is also 000. That means that these expressions are a relationship rather than a fixed point. For every 001, there's also a 002 and 3 and so on. We'll talk about this a bit more in the single crystal diffraction section later on. Back in the section on PLM, we discussed amorphous phases. An amorphous phase doesn't have enough order at the molecular level to diffract X-rays into the coherent beams that we see from crystalline materials. However, there will always be a few relatively common sets of spacings that might happen often enough to give a less coherent diffraction pattern. In these cases, the diffraction that results is quite diffuse and generates a couple of large rounded peaks, which we refer to as a halo because of how it appears as a ring on a 2-dimensional detector. I hope that helps clear up the role that crystallinity plays in X-ray diffraction.